In this module, we will continue with the discussion of the operating principle of squirrel cage induction machines, and we will see how voltages are induced in the rotor circuit, and thereby the currents flow and torque is produced. So that's why these machines are called induction machines, because by induction, electromagnetic induction, voltages and currents are induced in the rotor circuit because there is no such winding there, just a squirrel cage, which is not really supplied by anything other than through this induction. All right, so to understand induction machines, I think this transformer analogy is of extremely beneficial. So let's think of this transformer here with two windings, and I have purposely cut the core to sort of emphasize that in induction machines we have two air gaps. The flux path has to cross two air gaps. Okay, and initially let's assume that the primary winding has no resistance and no leakage inductance. That is similar to assuming no resistance and no leakage inductance for the stator winding, as we had done in the previous module here. So let's initially assume that load is not connected, and we apply a sinusoidal voltage to the primary, and as a consequence this magnetizing current would flow, and there will be this flux phi sub m in the core. So now this in the absence of any resistance and leakage inductance, this flux phi sub m is completely dictated by the voltage being applied and the number of turns we have in the primary. That's N1. Okay, that's Faraday's law, and there is nothing we can do to the secondary winding or on the secondary winding or in the secondary winding that will change this flux here. So if this flux, there's a time rate of change of flux, and that flux is linking with the secondary winding. So there's a voltage induced in the secondary winding, and if you connect a load across the secondary winding, there'll be current I2, and therefore there'll be an MMF produced by the secondary winding, which will try to influence or upset this flux phi sub m. But we agreed that it cannot change because it's totally dictated by applied voltage V1 and the number of turns, and the rate of change, the frequency at which the applied voltage is varying. So, this MMF that is produced by the secondary winding has to be canceled by additional current drawn by the primary from the input voltage here, I2 prime, such that flowing of I2 prime into the primary winding produces an MMF which completely nullifies the MMF produced by I2 flowing through the secondary winding here. And that's how the flux can get, flux remains unaffected by the load, and this is how the transformer primary knows that something has happened to the secondary winding, okay, because there is no electrical connection here as such, only a magnetic connection. And this is exactly what happens in an induction machine, as we'll see as we'll see later on. So let's look at how these voltages are induced in the rotor circuit. First, let's assume that the rotor winding is rotor bars are somehow open in the sense that there's no current flowing, just for the sake of discussion, and we are applying a certain voltages resulting in this stator voltage space vector, which is rotating at the synchronous speed, and it results in some magnetizing current which is drawn from the stator, and this flux density distribution is represented by the space vector, which is also rotating at the synchronous speed. But let's say that the rotor is rotating at a speed omega sub m, and this omega sub m is smaller than omega sinc. It could also be greater, as we'll see for generator operation. But let's say that omega sub m is smaller, so the rotor is slipping. That's why it's called slip speed. With respect to the synchronous speed, the rotor is slipping at this speed omega slip, which is the difference of these two speeds. So as you can see that these rotor bars are cutting this flux density distribution. The other way to say is that this flux density distribution produced by the stator is rotating at a speed faster than the speed at which these rotor bars are rotating. So there's a cutting of flux, and therefore in each bar there's a voltage induced, and at any angle theta, for example, as shown here, this is the flux density, because flux density is maximum along this axis over here. So this is the flux density, and then so at a bar which is located at an angle theta, this will be the voltage induced over here, making use of that fundamental principle that induced voltage is BLU. Okay, so you can see that in this picture, this bar over here under the maximum flux and this bar under the maximum flux, because the flux is like this, these two bars would have the maximum voltage is induced, and the bars away from this axis here, away from them, they'll be cosinusoidally smaller, these induced voltages. All right. So now we saw that there are induced voltages in the rotor bars, and these rotor bars are, actually short-circuited at both ends. And by symmetry, you can see that these both bars are at the same potential, and therefore the induced voltages are dropped across the rotor impedance. But let's assume that the rotor leakage is negligible at this point. Later on, we will include it. It's very important for certain applications to include the effect of rotor leakage. But let's assume that the rotor leakage is negligible. So there's only the resistance of the rotor bars, and these bars are short-circuited at both ends. So you can see that the picture is somewhat like this, where the induced voltages in each bar is different, and therefore, of course, the rotor resistance, the bar resistances are the same. So the amount of current in each of these bars would be different. And since the induced voltages are sinusoidally distributed, depending upon where these bars are located, the currents would also be sinusoidally distributed in these bars over here. So you can see that any bar has this current, which is given by the voltage induced in that bar divided by R bar. So we get this expression here, assuming that the rotor leakage is negligible, which is quite often the case for under the conditions these machines operate. All right, so let's see what happens. When we have currents in the rotor bars, they produce their own MMF. So this BMS was produced by the magnetizing currents that were drawn from the voltages applied to the stator, and in response to, which is of course rotating at omega sinc, but in response to that, there are induced voltages in the rotor bars, which are maximum here, and cosinusoidally distributed. Similarly, there are bar currents. So these bar currents also are cosinusoidally distributed, highest in these two, as shown here, coming out here and going in here, and then the bar currents drop off as you move away from this axis. So even though the rotor bar cross section in each of these bars is the same, these are drawn by different size circles to indicate that rotor bars are actually different, and therefore we have this sinusoidal distribution of currents, and which results in an MMF or flux, and we can apply a space vector vectors because these are sinusoidally distributed. So this is the flux density distribution representation produced by the magnetizing currents drawn from the stator. These are the flux produced by the rotor MMF due to the rotor bar currents. But like we agreed, just like in a transformer, the net flux here through the air gap cannot change if you ignore the rotor resistance, the stator resistance and the stator leakage inductance. So additional currents have to be drawn from the stator side to produce an MMF and flux which nullifies this flux which is produced by the rotor bars. Okay, and that's how stator of this machine knows that something is going on the rotor. So we can represent all this by a space vector diagram. We have this at some time 0. Let's say voltage A is peaking, so Vs is along A axis. The flux density space vector is over here. The magnetizing current space vector is over here. The MMF produced by the rotor bar currents is shown here, which is nullified by equal and opposite MMF due to the additional currents drawn from the stator, which we'll call Fr prime. And this is the currents that are additional to the magnetizing currents that are drawn from the stator side. Let's call them Ir prime. So the total current drawn from the stator phases can be represented by the space vector, which is the vector sum of Ir prime and IMS over here. So this vector over here. Okay, and of course the current those are drawn depend upon how much is the peak flux density here, and also the slip speed. Okay, so it's very important to recognize that the amplitude of these currents is proportional to slip speed. All right, so that's the space vector diagram. And so just to recapitulate recall some of the things here, we see that the slip is, there's a quantity called slip defined, which is the ratio of slip speed to synchronous speed. The slip speed is the difference between the synchronous speed and the mechanical speed, omega m. And if you divide that by omega sync, you get slip. And the slip generally in most induction machines is very low, between 1 to 3% of the synchronous speed. And similarly, the frequency of voltages and currents are at this slip frequency, SF, S times F. So F is the frequency of the voltages and currents in the stator circuit, and so in the rotor circuit, the voltages and currents are that frequency times the slip, which is very small. So in the rotor circuit, the currents are very low frequency, that like 1 to 3 hertz, like that here. And the main thing to notice is that what is happening is that all these space vectors that we saw in the earlier diagram, they rotate at omega sync. Okay. Whereas with respect to the rotor, the rotor space vectors are rotating at a much smaller speed, omega slip. But recognize that the rotor itself is rotating at speed omega sub m. So the sum of these two in steady state must be equal to omega sync. So all these vectors end up rotating at omega sync. So this is something very important to recognize for induction motor operation. And we can also calculate the torque because we have this magnetizing flux that was produced here. And then to nullify the rotor MMF, this IR prime space vector is drawn, which can be represented physically. Physical interpretation could be through this hypothetical winding. And there's a torque produced on this hypothetical winding, which will be in the clockwise direction, as you can see, but equal and opposite torque is produced in the rotor, which will be in a counterclockwise direction here. And that's in the motoring mode. This is also the speed of rotational direction here at speed omega m here. So we can actually calculate using the principle we have used earlier in case of PMAC machines what the torque produced is. And you can see that it is proportional to the square of the flux density peak and proportional to omega slip here, where omega slip is the synchronous speed minus the mechanical speed of the rotor. Okay, so that's, we can represent this torque speed characteristic for induction machines. Quite often it's shown this way, but if you want to put torque on the horizontal axis, this torque speed characteristic would look like this. But let's look at it this way, that, so omega m is being plotted here. When omega m is equal to the synchronous speed, there is no torque produced here, 0. But as the induction machine slows down, this omega slip becomes larger, and as omega slip becomes larger, more torque is produced. So that's basically and these curves are very linear up to this Tm rated over here, where it's reasonable to assume that the assumption of neglecting the rotor leakage inductance is quite valid. Okay, so trying to recall how these induction machines operate, if they are running at certain load and they are running at certain slip speed, if you increase the load, so if let's say load torque increases, then what will happen that the machine speed would come down. That means omega slip would go up. That means the voltage induced these bars would go up. That means the current induced in these bars would go up, and therefore the torque produced in these bars would go up. And eventually this torque produced at some lower speed would equal the load torque. Okay, so the operating point, which may be over here at certain speed here, may move to this torque over here and slightly lower speed. Okay. So it brings us to the conclusion of this module, where we saw the operating principle of induction machines, how the voltages are induced in rotor bars, how currents flow in the rotor bars, and how the torque is produced.